Welcome back to Aircraft Structures 1. This is Professor Anup Ghosh from Aerospace Engineering, IIT Kharagpur. We are in the lectures of 6th week or the module 6 in sequence. This is the 32nd lecture, and this is involved with the semi inverse method of solution. Semi inverse method of solution in terms of theory of elasticity approach to solve problems, and in that sequence we will learn how do we solve problem with a typical example. Now, in that sequence we always in every lecture I try to cover what we have learned so far. This time I will try to cover it in more brief as quickly as I can. History, aircraft development from a small one at Kitty Hawk by Wright brothers to the huge one like the AN 225. We have learned history of solid mechanics or structural analysis, or the way you say. Then various types of loads encountered or experienced by aircraft structure is discussed, where how those loads comes. And then we have learned the inertia loads play a huge role in design, and that in that context we have learned the flight envelope. And flight envelope also varies with respect to a particular type of aircraft depending upon its service condition. We have learned how can we find out from the overall external load the bending moment and shear force is encountered by wing and fuselage. Then we have learned 3-dimensional structures. We have solved a few problems in 3-dimensional structures with respect to landing gear problems, and then we have started the deflections energy methods. In that we have learned Castigliano's method, total potential energy method, complementary energy method, and we have learned a very good method, what I say that probably lays the fundamental foundation of future numerical analysis, that is the Rayleigh-Ridge method. To some extent in that discussion came the variational calculus, not that way, but anyway you are introduced maybe. So, and then the theory of elasticity got introduced to stress, then equilibrium with body forces, surface forces, stress transformation, concept of stress transformation. Our total discussion was predominantly in the Cartesian coordinate system. Then from there the principal stresses, how do we find a plane where there is no shear stress, and from there we have discussed that what are the properties of principal stresses, how invariant is observed. Then we have established strain displacement relation, then compatibility condition, how it is important. Without that solution is not practical, we need to satisfy the compatibility condition or equations. Then stress strain relations we have found out. Then in the last lecture we have covered the way how a problem is formulated and then solved. In that method we have already solved 2-3 problems with respect to the inverse method. In the inverse method we directly assume the stress function, Airy's stress function, and then we try to put the we try to find out the stresses, components of stresses, and then accordingly putting the putting the constants to 0 or modifying the constants, we can achieve some problem which represents the Airy's stress functions properly. So, with that note we will try to solve problems in theory of elasticity with semi inverse method. It is almost similar. We will use some conclusions like the pure bending portion, what we have learned in the semi inverse method part of the equation that we will be using to solve this particular example. So, before we go for the solution of the particular example, let us get introduced to the method. So, in this process what we do? So, disadvantage of inverse method, we are determining problems to fit an assumed solution, whereas in structural analysis the reverse is the case. So, that is quite obvious, but the solution may be simplified by looking at the shape of the boundary and the applied loading. Semi inverse method is popular in that sense, it is suggested by Saint-Venant. Semi inverse method is suggested by Saint-Venant. Here assumptions are made to stress or displacement components. But before we go, since Saint-Venant's principle is better to come across once. This is important, these lines are important, please I will read, I will try to explain with one example. In the next slide I will try to explain. I will tell you in very simplified words also, that will not include all these, but those are not totally correct. Simplification always sacrifices something. Anyway, if a system of forces acting on a small portion of a surface of an elastic body is replaced by another statically equivalent of force acting on the same portion of the surface, this redistribution of loading produces substantial changes in the stress only in the intimate neighborhood. It changes substantially, but in the intimate neighborhood of the loading, and the stresses are essentially the same in the parts of the body which are at large distance in comparison with the linear dimension of surface on which the forces are changed. Linear dimension of the surface on which the forces are changed. So, it says that if I replace by equivalent or statically equivalent force system, at the vicinity it is not the same case, but at some distance it is same, and that some distance is what? It is that distance is governed by this linear dimension of the surface on which the forces are changed. That is a principle, is really very important observation and noted by Saint-Venant. This helps us a lot. In the next page we will see how it helps us, but without looking into this thing, we have considered this in our mind and we have solved problems already in your mechanics, in your other say here also whatever we have covered during problem solving, we have assumed this. So, by statically equivalent systems, we mean that the two distribution of forces have the same resultant force and moment. So, let us see the example. So, by statically equivalent system, we mean that the two distribution of forces have the same resultant force and moment. So, what is shown here that if two P loads are applied at some section A, this is the distribution of stresses because of this two concentrated load at this point. But while the section is L apart, which is more than the B, it is uniform. That is what we always talk about, is not it? We say that load is applied at the tip of the member and the stress is uniform P by A. So, that P by A, here it is say if the area is A, then it is 2 P by A. So, that is what is said it in a different way. It says that if it is replaced by a force system, if it is replaced by many other forces summing up to P and statically equivalent, then it is same at a distance L where it is more than B. So, both the forces will induce similar type of stresses. With this context, with this understanding, we will move forward to our next slide, and in next slide we will solve a problem. This problem is quite popular from your first day of mechanics probably. Problem is similar, only difference is that we have assumed a different coordinate system. We have drawn the problem in a different way. The boundary condition or the fixed support is on the right hand side. At the center of the beam, we have assumed the origin and x is going this way and y is coming downward. So, with this consideration, we will do it is h, B, this is D. So, the section dimension. So, with this consideration, let us try to find out the solution. So, solution means stress as well as deflection. H is much less than the D. The loaded beam can be regarded as an example in plane stress condition. So, upper and lower edges are free from load and the resulting shear forces at x equals to 0 is P. So, there is no load on the upper and lower edge, there is a shear force, distributed shear force acting at this edge, which results into P. This is a boundary condition we will use later. We can see that sigma x x at any point of the section is proportional to y. Bending moment at any section is proportional to x. So, this sigma x s is proportional to y. This part already we have seen in our previous inverse method, and that brings us to this C 1 y cube by 6, and then B, a bending moment at any section is proportional to x, that is the reason x factor is coming here, and that governs this line's observation to our physical condition, gives us the way that this part is something like this. So, with this note, what we can do, we can start. Let us assume for a trial sigma x x is equals to C 1 x y, where C 1 is constant. So, this is same C 1 small or capital. We are following this, I jumped here to give you that observation, but it can have from this type of approach also, where following this y and x and y multiplication also we can assume, and then if we integrate that, what do we have? We get the same term what we have there, and we also have two functions f 1 x multiplied by y and f 2 x without any multiplication as two functions of x, because we are integrating the partial differentiation equation with respect to y, where f 1 x and f 2 x are known as functions of x. Now, the compatibility, it is satisfied, there is no doubt, but to satisfy this, what we get? We get one more relation in terms of f 1 and f 2. So, while we do this, if we carry out this term by term, I can again explain like the way I have explained earlier, but better you try once. So, with application or to satisfy the compatibility condition, what we have is that y del 4 f 1 del x 4 plus del 4 f 2 d it is a complete derivative, because these are only a function of x. So, with that note we move forward. Since f 1 f 2 are functions of x only, since f 1 and f 2 are functions of x only, the second term in the above equation is independent of y, but this must be satisfied for all x and y in the beam. This is possible only if this is equals to 0. This stating this is very easy, but it requires a lot of understanding or on the mathematical equations. If you think deep, you will also come to the same conclusion that these individually these two functions must be 0 to be satisfied by the grad 4 phi equation. Now, if we integrate all these terms, f 1 is equals to what we have is that C 2, C 3, C 4, C 5 and f 2 is equals to 6, 7, 8, 9. It is changing the power. I hope there is no point of explaining it. So, the phi changes with constants starting from C 1 to C 9, 9 constants we have to find out, and to find out those constants, let us see what do. We need to put the boundary conditions, but with these constants in place we can find out the expressions for sigma y y and tau x y. So, those expressions are quite obvious as it is shown here, and we try to put the boundary condition. This boundary condition is interesting. Sigma y is 0 at y equals to plus minus d by 2 for all x. If we go back to the previous equation, previous figure, we can easily observe that at this and at this, which are plus minus d by 2, definitely it is stress free, and that is the reason we say that this boundary condition holds. So, with this note we move forward. So, the boundary condition, as it is said in the last page, is repeated here, and we apply the boundary condition. Once we apply the boundary condition to sigma y y, we have see a very interesting one again, minus 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 minus, otherwise it is same, and again either I need to mathematically prove or I can simply assume that it holds and we can proceed. These equations must be valid for all x between 0 to L, x for 0 to L only when these constants are equals to 0. That is why it is made to 0, this. So, both the equations should hold only in case while these are individually equals to 0. These are proved in maths, we will not spend time for that, and consequently these 4 conditions, this is for this particular nature of the boundary conditions implementation equations, we get that C 2, C 3, C 4, C 7 are equals to 0, and then tau x y is equals to, we have minus of C 1 by 2 y square minus C 4. We have one more boundary condition, that is tau x y on y equals to plus minus d by 2 is also equals to 0. That is, it is also shear stress free. It is not only the normal stress free, the boundary at top and bottom, there is no shear stress also. This is a small correction, this is definitely not too equal signs, this is equals to 0. So, with that note what we see is that this gives us a relation between C 1 and C 4, and as I mentioned at the beginning while we were defining the problem that distributed shear stresses at x equals to 0, that means if we go back at this point, upper and lower edges are free from load and the resulting shear force at x equals to 0 is P. So, that is what we will implement now. This is implemented here, and if we implement that H is multiplied with to make it force. So, we with simple integration, substitution of the tau x y whatever we have this value and other things, and it yields that C 1 is equals to minus of 12 p by d cube h, and since I is already is quite well known, equals to minus p by I, and at the end all the 9 constants are known. Once we have all the 9 constants known, we can have expressions for sigma x as well as sigma y and tau x y. So, the tau x y reduces to the expressions are something like this, as we have if after implementation of the constants sigma x x is equals to minus p x y by I, sigma y y is definitely 0 everywhere, and tau x y is equals dependent on the y square, and accordingly we have. So, in the next portion we will try to solve the displacements. Displacements equations are interesting to solve, it is a simple mathematics now. There is not much of elasticity or structures, only boundary conditions are there. Boundary conditions in terms of mathematics you need to understand and you need to implement. So, keeping in mind what we have, the strain expression we put from the stress, what we have we integrate that. Similarly, for f sub y we have this expression, and gamma x y we have this expression, we name this as this 1, 2, 3. If we integrate, there will be unknowns definitely. So, we get g 1 y, g 2 x. So, with that, and definitely gamma also will be there. So, we can. So, we have found out by integration the del u and v. Here what we see that since it is a partial derivation of x. So, integration gives us a function of y, and g 2 gives us a function of x, and similarly we will be using this expression. So, incidentally one thing is, one typographical mistake is noticed, you please note that this is not multiplication, this is I should do it with red ink, blue is not visible, this is a positive plus sign. So, with this note please, I think it is you can also easily put it, and in the next slide while we will move we will use these equations, we will substitute these values there in the again these values in the third equations, and we will proceed further. So, we go to the next equation. So, substituting in 3 equation 3, what do we have, and little bit rearrangement definitely we have, that is the reason we have partial derivative with respect to y, and we have also the other term with respect to x, and it is rearranged a little bit. I hope you can easily carry it out, and then the left hand side is a this rearrangement is done to with keeping in mind with the things that all the y terms are kept on the left hand side and all the x terms are kept on the right hand side. So, the left hand side is a function of y and right hand side is a function of x. A function of x can be equal to a function of y for all values of x and y only when they are both equal to constant. That is quite obvious. This phenomena we will be using in many part while we will go for the higher stages of say any course, say it is if it is CFD or dynamics, structural dynamics or anywhere. So, anyway this is a mathematical phenomena and according to that we assume that it is a constant A. Okay. So, we put this is equals to A1 and that is the other side also is also equals to A2 and again we rearrange. Once we rearrange and integrate we get G1 and G2. We have two more constants because of integration, that is A2 and A3. So, all total we have 3 unknowns again, fine. So, we need to find out those 3 unknowns. How can we find out those 3 unknowns? We are in the process of finding displacement, all functions are in terms of u v. So, we need to put boundary condition in terms of u and v. So, while we put in terms of that u v the boundary condition, what we can see, let us see. So, then the displacements are u v as it is put as A1, A2, A1, A3 all the constants u v is completely written here and the boundary conditions at x equals to L and y equals to 0. That means, at this point as well at this point the other x equals to L, sorry not at this point, at this point x equals to L, y equals to 0. Here u v, u equals to v equals to del v del x. That means, the slope is also 0 because the structure is supposed to bend like this. This slope is always 0, these are 0. So, with that implementation of 3 boundary conditions easily we can find out A1, A2 and A3 and if we solve those what do we get is that A1 is equals to P L square by twice E I minus 1 plus nu P d square by 4 E I, A2 is equals to 0 and A3 equals to P L cube by thrice E I. And if we substitute those values, A2 is 0. So, this is A y function is there and we just put it here and in a different way and we also put the v boundary condition and the deflection curve for the neutral axis. Since it is neutral axis, which parameter goes to 0? That is y equals to 0. So, v expression y equals to put to 0 and we have this expression only. So, this is the equation of the deflection line, this is the line we are talking about. So, this is equation of this line. Okay. And one more interesting point, probably you have solved using various methods, that the tip deflection is always P L cube by 3 I. So, that if you put x equals to 0, this goes off, this is also equals to 0 and we have the desired solution is equals to P L cube by 3 E I. So, with this note the preliminary discussion of theory of elasticity ends and in next 2 weeks we will solve specific problems with help of theory of elasticity. We will see how it is important, how does it gives insight to a certain problem and accordingly we will learn a lot. So, we have come to the end of today's lecture. In this process the usual the reference slide comes And also comes the conclusion page, where we have learned that semi inverse method of solution using one example of cantilever beam. And with that note, I thank you all for attending the course. Thank you.